So those studies were done by many people at Mercator, and we are also relying on the people who are setting up the new systems to show us how it works. So I will first give you the motivation of looking at the impact of observation on our systems, and that gives you some different approaches used to test the impact of the present altimeter constellation, and also the future mission. And I will, in fact, show you a few slides on the impact of Argo floats and conclude. So I quickly recall the context that Jean-Michel gave us before. So we are running a system which relies on a model, and we try to correct this model towards the more observed reality with in situ and satellite data. So why we are trying to assess the impact of observation in our system? It's because the quality of our analysis and forecast highly rely on the quality of the observation. We also need them to be available in real time. And we need to know quite precisely the error observations. So the impact studies allows us to better understand the role of each component of the observation network in constraining our solutions. It's also a way to prepare the next generation of system to assimilate new data. And at the end, we also try to draw recommendations from our operational point of view to space agency and in situ data providers to guide their future evolution. So to do those studies, we are using different approaches. So maybe you know some of them. So it's the OSSE, what we call the OSSE, it's Observing System Evaluation. We compare two simulations, exactly the same, except that we resolved one data set in the later one. So we can compare the changes in those simulations, and it can be attributed to only the change of the observation network. So this works for already existing observations. So in the case of future observation, we need to simulate them with a model, and then we assimilate them in another one, and we compare the two simulations. There are also other approaches, such as the forecast sensitivity to observation, the degree of freedom, but I won't speak too much about those ones. And we also need to analyze the result of such experiment. We need to define diagnostics. So the first one are really internal assimilation diagnostics to check the success of the assimilation. And after that, we look at more physical diagnostics and also related to the process that are supposed to be well observed with a given network. So here it's an example. It was done with the current and not the new system, the current system at 1/12 of a degree in the North Atlantic. The idea was to look at the impact of altimetry constellation. So we did several experiments with a different number of altimeter assimilated. All the other usual data were still assimilated, in situ data and SST. So, I don't know. Okay. Whoop. So on the left, I show the maps of the difference between different simulations. On the left, it's the difference between the simulation without any altimeters and with one altimeters assimilated, JSON2. So we can see the impact on the SSH of the use of one altimeter. So we can clearly see large differences in geographical differences, with the largest pattern in the Gulf Stream areas or in eddy energetic regions. And on the right, it's the same diagnostic, but between the simulation with 3 altimeters and 2 altimeters. So once again, we see the same region, but the amplitude is smaller. So here we looked at the changes in our analysis. We now need to check if those changes correspond really to an improvement towards the observation, that the misfits are reduced. So on the left, it's a kind of view, statistical view, to see how the error is reduced when we increase the number of altimeters. So on the 0 represent our kind of best estimate with the analysis with 3 satellite altimeters, and then we show in percentage the error which increase when we remove one by one the satellites. So so we will go from right to left. So 0 when we have all the satellite analyzed, then the purple bar, it's about 5% when we remove one satellite in the analysis, and then another one. And in red, when there is only one satellite remaining. And on the left, the bars represent the errors for the forecast. So we see that the errors are larger for the forecast, that is expected, and larger when the number of satellites is lower. And another thing is that in purple and green, it's experiment with 2 altimeters removed, but not the same. So we can see then the impact is also depending on the orbit and error of the satellite we consider. So on the right panel, we also checked that the reduction of errors on the SSH when we assimilate altimeters also improve, or do not degrade at least, the temperature field and salinity on the entire water column. So the profile are representing the RMS and mean of the errors for temperature and salinity, and we do see that it's slightly improved, but it's nowhere degraded. So here it's another different example on altimetry, and it deals with the future SWOT mission. So SWOT will provide not only like the nadir altimeters kind of aligned observations along the track, but across track information with a large source of 100 kilometers. So to test and to prepare our system to assimilate such data, we simulate them with a regional model. So here it's really a small zoom showing on the left the SSH of the model. So from this one we extracted simulated SWOT tracks. So it's in the middle. And on the right we can see the equivalent of what is currently existing as nadir altimeters. So the 2 right panels, it's for 1 day observation. So the way of looking at the ocean is clearly really different between those 2 altimeters. So there were then an evaluation of how such new technology can constrain our solutions. So here, as we have the full true ocean from where the observations were extracted, we can compare it with the simulation where we assimilate those simulated data. So here it's the correlation between what is called the nature run, where the observations were computed, and all other kind of OSSE experiments. So the first one is just the free model without any constraint compared to the nature run. And sorry, for the colors, it's the correlation that were computed over the experiment. In the middle, it's, sorry, I think I switched the 2. In the middle, it's the nature run compared to a 3 nadir altimeter experiment. And on the right, it's when the SWOT data are assimilated. In fact, we found that SWOT constrained much better the gradient in our system and allow a better representation of the SSH. But it's still an ongoing work because the errors in SWOT are quite complex, and we need to take that into account more precisely. Here's just a quick example. There are other approaches to trying to estimate the impact of the observation in the system, and some of them do not require to remove the observation, which can be a kind of disequilibrium when you do that. So here I show the degree of freedom of the system. It's widely used in the meteorological community. So the idea is to quantify the number of independent direction constrained by each observations. So in fact, it's the sensitivity of the analysis at the observation point to the observation point. It's also a way to measure the information content that was effectively extracted from the observation by the analysis. And we can use what is called the information content, the DFS divided by the number of observations. So 1, if it's close to 1, it means that the observation is fully used. And if it's close to 0, that it's not really used. So it could mean that it's redundant or not well used by the system. So on the left, we see that we computed the relative weight of the different altimeters with these metrics. And it was done with the previous system. So we can see on 2015. So we can see JSON2 and Altica, which are the most important altimeters for the analysis, and Cryosat and HY2, which are less important. So that's for all what I've showed before, and this one especially, the results are really sensitive to the tuning of the system. So we need to redo those calculations in the new system, and they can give slightly different results. So on the right, it's another way to look at those quantities with maps. So we see that observations are really important, and their density is probably important, like in the western boundary quadrants. And in other regions, it seems that they are slightly, they can be redundant. But this is the case for Psi3, which is a 1/4 of a degree system. So it's not the same answer with the 1/12 of a degree. So to conclude, we've seen that the sensitivity of our system to observation highly depends on the region, that an increased number of data allows a better representation of the SSH, and water mass also. I will give you some details. And we also checked that the impact on the non-observed variables was they were not degraded. So those studies help us to better understand the constraint of the observation in our system, but they really need to be carefully set up and analyzed with appropriate diagnostic. And like I said before, conclusion highly depend on the system setup and configuration. So the conclusion need to be really carefully translated into requirements for the observation networks. We are involved in different projects dealing with the observation impact studies. So some of them on altimetry with ESA, for example. We have an ongoing study on large source altimetry, the data assimilation of surface salinity observation. For the in situ network, we're involved in a European project called Atlantos. And in that case, we're working with different other Copernicus systems, and different method will be used. But we still want to share the simulated observation we will be using. And the idea by using different methods is to get more robust conclusions. We are also working closely with CNES. Most of the results I show are coming from studies we're doing with them. We're participating to the SWOT science data team. And of course, we have a strong link with the Good Ocean View OSSE, OSSE task team. So thank you, and this is a slide for Alex.
Thank you, Elisabeth.